hard to remember. Like,
Okay, finishing off rational functions. Two loose ends after that first video. In this video, do the another whole example. Go through all those steps again. See everything that happens out of there. And then try to have one more weapon. It seemed like we were one weapon short in that last example, and I want to show that weapon off in this example here. And then another loose end was, I mentioned in the other video, that domain issues don't have to be vertical asymptotes, and I got to tie up that loose end before we're done. Okay, all the steps from the beginning. Start with domain issues. Domain issues, we can't have the denominator equal to 0. So I can't x cubed minus 2x squared minus 5x plus 6 can't equal 0. So I got to do some factoring here. Let p at x equal x cubed minus 2x squared minus 5x plus 6. Try some different values. Try p at 1. 1 minus 2 is negative 1. Minus 5 is negative 6. Oh, that works. Therefore, x minus 1 is a factor. K equals 1. 1, negative 2, negative 5, 6. Bring down the 1. 1, negative 1, negative 1, negative 6, negative 6, 0. Very good. That went pretty well. So we have x minus 1 times x squared minus x minus 6 can't equal 0. And I get x minus 1. I guess x plus 2, x minus 3 can't equal 0. Therefore, x can't equal 1. X can't equal negative 2. And x can't equal 3. 1, negative 2, and 3. Now, I said in the last example, I like putting those on my graph right away. Put my graph all the way down here. I'll put them in gray because you don't want them too dark. You don't want them to mess up your whole graph. And what did I say? X can't equal 1. X can't equal negative 2. And x can't equal 3. Put those on my graph. Those are vertical asymptotes. The graph can't pass there. So really, I divide this thing into 4 sections. I want to know what happens left of x equals negative 2. I want to know what happens between negative 2 and 1. I want to know what happens between 1 and 3. And I want to know what happens between 3 and 6. I'm laying the groundwork for my last big weapon that I'm going to show you here. But now I got some idea of what's going on with the graph. It's broken up by these vertical asymptotes. That was domain issues. What was next on the list? Got to memorize the list. Got to know what these things are we're going to look for. The next one is, did I leave enough room there? Yes, I did. X-intercepts. And for x-intercepts, we set y equal to 0. So y equals 0, I get 0 equals, listen, we got to progress past this, writing down the whole denominator thing. If I write 0 equals x squared over x cubed minus 2x squared minus 5x plus 6, that whole denominator is going to come over and multiply by the 0. I'm going to get 0 equals x squared. So I get an x-intercept of 0. Let me put that on my graph. That really helps. It doesn't seem like a big deal, but it really helps. It really tells me a lot about what's going to happen between negative 2 and 1. It's going to go through this 0. It's going to approach these two asymptotes. Is it going to approach them upwards, downwards? Well, I don't know. Hey, my big weapon's coming. Let's not worry about that too much. But that x-intercept really frames what's going to happen in the middle there. Y-intercept. Set x equal to 0. So I look at this thing, and the top I get 0, and the bottom I get 0, 0, 0 plus 6, so I get y equals 0 over 6. I get a y-intercept of 0. Well, that's not very exciting. That's not any new information, because that x-intercept of 0 is the same as that y-intercept of 0. Okay, domain, x-intercept, y-intercept. Good. Next things, asymptotes. End behavior really was I'm looking at. And so I look at the degree of the top and the bottom, and I analyze what's going on here. And I see the degree of the top is lower than the degree of the bottom. And you can memorize those rules I introduced in the last chapter, or you can just know what's going on here. If you sub in a big x value, the top's going to get really big, but the bottom's going to get so much bigger, you're going to be dividing by something that's really big. And so you're going to get a horizontal asymptote. y equals 0. And I'm going to put that on my graph, but just a little hint here on how to draw horizontal asymptotes. Vertical asymptotes should go all the way down the page like that, because vertical asymptotes are these stop signs. You cannot go through them. And so horizontal asymptotes, they have a similar name, and that makes people think you can't go through them, but you can. Horizontal asymptotes are just end behavior. So when I draw on horizontal asymptotes, I just draw them out here at the ends here, just to remind myself that I've got to approach that as I get to the outside. Oh, I didn't use gray pen there. I used that pencil. I sort of like the way that came out. Okay, but I'm going to go back to here and get that on there a little darker. Horizontal asymptote at y equals 0. See, I didn't draw it all the way across. You can draw it all the way across, but don't get excited if you have to go through it. You can go through horizontal asymptotes. They're just end behavior. But vertical asymptotes are domain issues. You're not allowed to go through them. That actually helps here, folks. Let me just do a little forward thinking here. I got this asymptote here and there. It's sort of either got to do like this, or it's got to do something like that, because it's got to approach the asymptote. So I sort of know what might happen here, but it's not clear exactly what's going to happen here. I need some more weapons, and I'm going to show you some more weapons in a minute. Is that disappearing there? Slowly but surely it's modifying my screen. Are they all gone there? Okay, yeah. So I don't know exactly what's going to happen out there, but I have some feeling for what might happen in there. Okay. Horizontal asymptote y equals 0. Oh, that's all the stuff. That's all the weapons, right? And if you're looking at this, you're like, well, that's really not much. Oh, it's a ton. Let me tell you, that's a ton of information. But we need one final weapon that pulls it all together. And the final weapon is a positive-negative chart. We mentioned positive-negative charts in previous chapters, but we didn't do too much with them. Now they're invaluable. If you do a positive-negative chart of this, it all becomes perfectly clear. Let me talk about what you need for your positive-negative charts. To build a positive-negative chart, I'm going to build it right above here. I have space for it. I want to talk about what's happening before I get to -2. Then I want to talk about what's happening between -2 and 1. Then I want to talk about between 0 and 1, between 1 and 3, and greater than 3. So my chart, positive-negative chart, should have x-intercepts on it and vertical asymptotes. Those are the two things I got to use on my chart, because those are the times that this thing can change from positive to negative. Think about that for a second. The only way to change from positive to negative on a graph is to go through an x-intercept or have a vertical asymptote as a domain issue. So what were the x-intercepts? The x-intercept was 0, and I had these vertical asymptotes. So I want to talk about what happens before the first vertical asymptote, which was -2. So I'm going to go, okay, I want to know what happens before I get to -2. Then when I want to talk about what happens between -2 and the next thing, which is 0, I got to look between -2 and 0. Then between 0 and 1, then between 1 and 3, and then greater than 3. You can actually get all that stuff right off the graph. Now, in the completed version of the note online, it goes through each of these pieces very carefully, but I'm going to show you a little faster way to build this table that I think you can follow. You can get all that stuff right off the graph. You can look at the graph if you're looking at where I put the vertical asymptotes and the x-intercepts. You can see, oh, I want to look at before the -2, between the -2 and 0, between 0 and 1, between 1 and 3. I want to know whether it's positive and negative in all those sections. And if you're like, why do I want to know what's positive or negative? Just watch. Let me build the chart, and then you'll see. So this function that I'm trying to graph has an x squared on the top, and on the bottom has these factors, x minus 1, x plus 2, and x minus 3. And in each of these sections of the graph, this graph is going to come out to either positive or negative. Let me walk through how I decide whether it's positive or negative. I'm going to need another color here, blue. I'll go with blue. So to decide what's happening for less than -2, what I need is a number to represent that section. To say, you can pick any number less than -2 to figure out whether this thing's going to be positive or negative in that section. I'm going to use -3, very close to -2, but it doesn't have to be. I could use -5, -10, whatever. Now, look at the numerator. If I sub -3 into the numerator, it's going to be -3 squared. That's going to be positive. I don't really care what the value is. All I want to know is that it's going to be positive. And in the denominator, it's going to be, okay, so negative 3. When I go negative 3 minus 1, that first factor is going to be negative. Negative 3 plus 2, that second factor is going to be negative. And negative 3 minus 3, that third factor is going to be negative. Let's talk about this. The denominator is going to be negative because 3 negatives multiplied together will give negative. So then I'm positive divided by negative. This whole thing's going to be negative, and I drew it really big. For x less than negative 2, this thing's going to be negative. I can draw the graph for this section. I know exactly what's going to happen. It's got to be negative. It's got to approach this asymptote. Oops, I wanted purple there. To get rid of that? Yeah, okay. Purple for my graph. It's got to approach this asymptote, and it's got to approach this asymptote. And it's got to be negative. My positive negative chart told me it had to be down there. That was the big decision. Is it going to be above 0? Is it going to be below 0? You see how the positive negative chart tells you exactly what to do. Next, between negative 2 and 0, I need a representative number in there. Back to my blue. Careful here. I'm going to use negative 1. When I put negative 1 into the numerator, I go negative 1 squared. That's going to be positive. The denominator is going to be, let's see, negative 1 minus 1 in the first factor, I get negative. Negative 1 plus 2 in the second factor, I get positive. And negative 1 minus 3, I get negative. The denominator is going to come out to be positive. A negative times a positive is negative. Times another negative is positive. So I'm actually going to get positive over positive here. In this section, between negative 2 and 0, the function is going to be positive. Back to here. Between negative 2 and 0, it's got to be positive. Well, if it's going to be positive and approach this asymptote, it's got to look something like this. See? The positive negative chart just completely demystifies everything and tells you exactly where to draw the function. I'm going to finish the rest of the table, and then I'll come back and do the graph for there. Between 0 and 1, ooh, tough section. I got to think of a fraction. I'll think of 0.5 between 0 and 1. Top will be positive, bottom will be negative, positive, negative. And I did that one fast on purpose to try to motivate you that once you get good at these, which I'm really not doing anything fancy there. I'm just in each factor putting the number in and seeing if I get positive or negative. Once you get better at it, that can go very fast. So if this seems like it's taking a long time, it won't take you a long time to build these charts once you get better at them. And the function's got to be positive in that section. Very interesting. Maybe that's not what we expected to happen. But the algebra says very clearly that that function comes back and is positive in that way. Maybe we knew that because it's x squared. It's a double 0. It's also a turning point. Maybe not. That's maybe not all clear just yet, but we did mention that in previous chapter. Now between 1 and 3, I'm going to use the number 2. It's the obvious number to use between 1 and 3. And let me just go through it slowly again so that you can see the thinking, and then I'll do the last one fast so you can be motivated that it can go quickly. Okay, so I put 2 in the numerator. I get 2 squared, which would be a positive number. In the denominator, the first factor is 2 minus 1, which would be positive. Then 2 plus 2, which is positive. Then 2 minus 3, which is negative. This whole thing's going to come out to be negative. Between 1 and 3, this thing's going to be negative. Oh, between 1 and 3, it's going to be negative. So it's got to approach this asymptote here. Oops. Did that again with the colors. It's got to approach this asymptote here. Because where it says it's negative, it's got to approach this asymptote here. So apparently it's got to come up and hit some maximum and come back down like this. Do I know where the maximum is? No. In this course, we won't know exactly where the maximum is. And so we're just getting the shape here. I'm telling you, calculus will solve this problem, so don't worry about that too much. We'll deal with it. Could it go through the x-axis? No, it cannot, because we didn't have other x-intercepts, so it can only go up that far. Last section. I'm going to do it quickly, not to show off, but just to show that this method can be done very quickly, so that you don't have to think that this has got to take forever once you practice it. X greater than 3, I'm going to think of a number like 5. 5 squared is positive. 5 minus 1, positive, positive, positive. They're all positive on the bottom. This thing's got to be positive. As far as my graph is concerned, it's got to be positive the whole time. It's got to approach these asymptotes, so it's got to go something like that. There's the full steps. That's tying it all together into one example. Okay, only thing left was this vertical asymptote thing. There is one time that you won't get a vertical asymptote. And it's a huge idea that's going to take a while to develop. We really, really need it for calculus. Here's when it happens. I'll come back to this explanation here in just a minute. I'll just talk about this thing. And I'm not going to sketch the whole graph, Well, actually, I will. I'll talk about what the graph of this thing would look like. F of x equals x squared minus 4 over x minus 2. If I just factor that numerator, here's what happens, and here's what happened a lot last year is you did a lot of questions like this where you factored and canceled, and this one cancels. And something very interesting happens here. I'm getting addicted to this gray colors. Get rid of those. And so f of x equals x plus 2, except x cannot equal 2. What could that possibly mean? I'm going to do a little freehand graph of this because I didn't put a grid on here. See how I do. Whoops, that didn't go like I wanted. The whole iPad moved when I tried to do that there. So a little straighter action here. Here's y equals x plus 2. Now, a lot going to happen here in just a short period of time. The function x squared minus 4 over x minus 2 is the function f of x equals x plus 2. If you want to graph x squared minus 4 over x minus 2, you just graph y equals x plus 2. And so y equals x plus 2. I'm not trying to draw a perfect graph of this, so don't get too wound up about it. Just need a little bit like that. It's going to look something like this. Y equals x plus 2. Something like that. And your immediate reaction should be, this complicated rational function, x squared minus 4 over x minus 2, is just the line y equals x plus 2? Mostly. It almost is. That graph is the graph y equals x plus 2, except for this. X cannot equal 2. So if I go out to here and say, okay, at the x value 2, and this is going to blow your mind in just a second, at the x value of 2, which is going to be like a y value of 4, that x value can't exist. But it's not a vertical asymptote because we're talking about a line here. So here comes my eraser. Is it going to let me erase just a little piece there? Oh, no, it's not going to. Oh, that's okay. I'm up for this. I'll go for a pen. I'll get a white pen out here, and I'll go, okay, right there. That's what happens. Weird. There's a hole. And that little circle I put on there is not part of the graph. It's just trying to draw people's attention to the fact that there's a hole in this graph. What a shocking result. Here's what's happening. And it comes from the restrictions you worked on last year. When you cancel out a factor like that, that factor represents a hole in the graph. I've simplified the graph a lot, that this very complicated function became a very simple function, but then I had to poke a hole in it at that specific x value. That's what that restriction was telling you. So there's two possibilities for restrictions. One is it's a vertical asymptote. The other one's a hole. How will you know? When it cancels. Cancels? It's a hole. That's how you'll know. So when you factor it and cancel it, and you're going to factor it anyway. So when you go through them, you're going to factor it anyways. And when it does factor and cancel, you got a hole. And that's what it's saying above here. A rational function right up here. A rational function f of x over d of x has a hole at a if you get 0 over 0, basically. And they have a common factor. That's the part I want you to remember of x minus a. When that has a factor the same, the top and bottom, when those two factors cancel out, you have a hole there. Okay, folks, that's a giant lesson with some giant homework. So the next period is just a work period to try and work through some of those ideas. You have to follow up with questions. You have to keep looking back at these details. Chances are you're going to watch that video, then you're going to go back and watch parts of it again. Hopefully, you'll be able to stream it back and forth and find the spots in the video you want. Maybe after watching it, you're going to be like, oh, maybe I should actually copy all that down once. There's a completed version of the note there that you can just print out, but I really suggest you writing that stuff out because it really does help to write it out once. Lots going on there, lots of homework to do. This stuff isn't impossible, but there's a lot of details to work through. Some study pages would help. One study page that might help is a reminder of all the steps that we did to graph. Steps to graph. Where did we find? We found the domain. We found the intercepts. We found asymptotes. And then we built a chart. And so you might want to come up with an acronym to remind yourself to do all those things. DIAC. something silly. Don't invite, careful, any Amy's in our class? No, no Amy's in our class. Don't invite Amy canoeing. You can make up your own acronym, but come up with something to remind yourself of those 4 big steps. And don't let me confuse you that that's just, oh, now it's simple, just those 4 steps. Each of those steps had their own steps within there, but that at least gives you the broad categories. Okay, folks, get to work, knock this stuff down, get in touch when you have trouble with it, and have a great day.